Okay, this is Miss Cater, and we are going to do a tutorial on electron configurations. We did the Hog Hilton a couple of days in class last week in my pre-AP classes, but I want to come back and just have a little review session on that. I don't know, I want to make sure that we understand the rules for electron configurations, and when we use that term, what exactly we're talking about. Now, if you remember, when we did our Hog Hilton activity, we said that there were 4 rules that we used to fill up our weird hotel. Remember, our hotel started at the bottom with, on the first floor we had an S room, on the second floor we had a 2S and we had 3 2Ps. On the third floor we had a 3S, 3P rooms, and 5 of the itty-bitty D rooms. And you can just continue to go up from there, but that's as far as we really needed to get. And the 4 rules were, first off, they were lazy, so we fill the lowest level first. Secondly, they don't like each other, so when it came to filling up a P room or a D room, you put 1 pig in each first before you paired it, because they'd rather fill up the lower levels first again. But if possible, they would like to be them by themselves. Rule number 3 is that since they don't like each other, they face opposite directions. And then the last rule is that they stink, so we can only put 2 in each room, or each blank. Each one of those blanks represents a room in our Hog Hilton. Well, our electrons going into atoms are basically the same analogy. The electrons are going to fill the first level first. They'd rather fill 1 in each P before they come back and pair up and get a roommate. If there are 2 in the same room, they're going to spin in opposite directions, and they can only have 2 per room, 2 per blank. So let's look at a couple of examples. Let's say that I have the element carbon, and I look on my periodic table, and the element carbon has an atomic number of 6. That means that it has 6 protons and 6 electrons. Now, the way I'm going to put those 6 electrons into the atom, or in my Hog Hilton, if they were hogs, is I would start on the bottom floor with the 1S room. Then I would move up to the 2S, 2P, then the 3S, 3P, 3D. Okay, so I'm going to start at the bottom. 1, 2, 3, 4, 5, 6. Okay, so I put 1 in each of these blanks before I come back and pair it. That's one way that I can write an electron configuration. Another way I can write electron, actually this is called orbital notation, but it's one way that I can tell where electrons exist in an atom. The other way I can do it is with the electron configuration, where instead of drawing these boxes and these arrows, I write it like this. 1S has 2 arrows, so I put a 2. 2 arrows, subscript of 2. And then I do a 2S, 2. Again, I have 2 arrows, so I put a subscript of 2. And then a 2P, 2. 2 arrows, subscript 2. This is what is referred to as electron configuration. It's just a big fancy way of telling me where we think the electrons are in an atom of any element. Okay, let's look at another example. Let's try sodium. Sodium on the periodic table, atomic number 11, means that it has 11 electrons. I'm going to start at the bottom, always the same pattern, 1s, then 2s, then 2p, then 3s, 3p, 3d. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. The electron configuration notation for that would be 1s, 2, 2s, 2, 2p, 6, because there's 2, 2, 4, 6, and then 3s, 1. Now we talked about Lewis dot structures here recently this week too, and we said Lewis dot is the number of valence electrons, and remember valence electrons are those in the outermost shell. Well, for sodium, the outermost shell is the 3s, and I have 1 electron in there. So that's why my Lewis dot would be Na with 1 dot. All of this that we've been talking about kind of works together. It's all different ways of telling me where electrons are in the atoms. And it's these valence electrons that are responsible for a reaction. Those are the ones that get moved around. Let's do another one. Let's pick neon. Neon is atomic number 10, and it has 10 electrons. So I start at the bottom, 1s, 2s, 2p, 3s, 3p, 3d. Okay, now let's talk about our rules. We start with the lowest level first. Okay, so we fill lowest first. That's called the Aufbau principle. It's just named for the scientist who discovered it, whose last name was Aufbau. Okay, so 1, 2, 3, 4, 5, 6, 7. Then I put in 8, 9, 10. Filling each P or D before pairing is known as Hund's rule. Again, name for a scientist, Hund. Hund's rule says you fill each P or D first before you pair it. So if we relate that to our hogs, it's the hogs don't like each other, so you got to put 1 in each room first before you come back and fill it up with the second one, because they'd rather have a roommate than have to go up to that 3rd floor. Electrons, same thing. They would rather pair than have to move up to the next energy level. The electron configuration for neon would look like this: 1s2, 2s2, 2p6. You'll notice all of my exponents add up to the number of electrons in the atom, which in this case is 10. 2 plus 2 plus 6 is 10. Try a couple of examples. So here you're going to turn this in Google Classroom. I'm going to write the question here, and I've also put it on my assignment notes there, so make sure you read those notes. And here is your question. I want you to give the configuration both ways for hydrogen, lithium, and calcium. Okay, have a great evening.